All right. Okay, we're live. Good evening, Europe, and good morning, US. I'm happy to welcome you to another grand talk within the module Emerging Fields in Architecture. Today we talk about space architecture, and Marc Cohen is here to tell you more about the continuum of space architecture. Marc Cohen is a licensed architect who has devoted his career to founding and developing the field of space architecture as a scholarly and scientific discipline. He worked at NASA Ames Research Center for 26 years and then at Northrop Grumman for 5 years. After that, he ran his own business, which is called Astrotecture, for 7 years. Along the way, he picked up degrees, master degrees and doctoral degrees from Princeton, Columbia, and Michigan. I myself have met Marc Cohen for the first time when he led the organizing effort to hold the landmark very first Space Architecture Symposium at the 2002 World Space Congress. At this symposium, the attendees established the Millennium Charter for Space Architecture, which is still valid and cited today. In today's talk, he will give you an insight about his work and also about his way of thinking. Marc Cohen's work intertwines with NASA goals and objectives, especially for human exploration. When I talk about him, I often refer to him as a walking library because he has published an immense amount of technical papers related to space architecture and engineering. His early contributions, for example, include the cupola and the spherical nodes for the International Space Station, the Suitport EVA access facility for the International Space Station and lunar planetary surfaces, and the Space Station Proximity Operations Simulator. Marc Cohen also developed a Suitport concept and received an US patent for it. Since then, this patented Suitport concept has been widespread and found adoption in the space architecture community. In 2022, Marc Cohen received the Gordon Woodcock Award, which is the highest award an individual can achieve for professional excellence in space architecture. Marc, I'm very glad you're here today to talk about why space architecture needs an architecture theory. Thank you so much for coming. The floor is yours.
Thank you. I didn't remember I did all those things. Okay, so the topic for today is the theory of space architecture, the continuum from Earth to orbit. And the real purpose of this talk is to start talking about theory related to space architecture. And the continuum from Earth to orbit is a piece of that theory. It's the largest part of this talk, but there are many other aspects of theory for space architecture. So next slide, please. You have to get rid of this meeting is being live streamed. Can you hear me? Sandra, do you hear me?
Yes, I can hear you. Can you hear me?
Okay, there's this sign up in front of the screen, which is...
But it's only in front of your screen. It's not...
You have to remove that.
It's only in front of your screen, Marc.
Oh, well, that doesn't help. Okay, all right, so let's go to the first slide. First slide, please. Okay, we have introduction. Okay, so the intent of this presentation is to begin introducing the idea of developing a theory of space architecture. Some people might argue that most of my work is theoretical. I know Chris Kennedy at Johnson Space Center thought I was mostly theoretical and not practical. And it's partially true that a lot of my work does have a theoretical basis. And so I break my space architecture work into three major overlapping phases. The first was design, which I was focused on for about 25 years, and then research, which is still sort of ongoing, but I'm doing less of it. And then the third phase is really a focus on theory from about 2010 to the present, whenever the present is, whenever that occurs. Okay, next slide, please. So I'd like to read you a definition of architecture from Richard Neutra, an architect who's done some very famous works in Los Angeles, particularly. So architecture is a social art. It becomes an instrument of fate because it not only caters to requirement, but also shapes and conditions our responses. It can be called reflective because it mirrors a program of conduct and living. At the same time, this art of a planned environment does more. It also programs our daily conduct and our entire civilized life. It modifies and often breaks earlier established habit. So, to my way of thinking, this definition of architecture is largely philosophical and theoretical. I mean, it has a practical side to it too, in terms of what the practice of architecture actually does if you're designing a building for a family or a company or an institution. All of those things that Neutra discusses can be part of it. But what is the higher level? What is the superstructure or the overarching umbrella for this approach to architecture? Okay, next, please. So I'd like to say a little bit about the design methodology. First of all, design of space architecture occurs often in a condition of ambiguity, irresolution, and uncertainty. That is to say, there's always a lot of unknowns about the requirements, about the capabilities, about the cost, the budget, the launch vehicle, and so on. And that's why we often see many different alternative solutions to a space architecture design problem. The second idea here is that a design solution, especially a schematic design solution, constitutes a hypothesis about what the design problem is. Because of the fact that there is so much ambiguity, irresolution, and uncertainty, it's often the case that in space architecture that there isn't a simple, clear-cut design problem definition. The design problems can be described as ill-structured and or ill-defined. And then the third point is that selecting a successful design solution, and I mean only if it's successful, sort of reverse engineers the design problem to, in effect, redefine it and to restructure it in a way that enables the design solution to succeed. Okay, next slide, please. So in this talk, the scope of our space architecture theory is going to cover 5 projects. These projects are participatory design of the space working environment, which is the one that was on the poster, testing the Celentano curve for habitable pressurized volume, the continuum of space architecture from Earth to orbit, which is sort of the major portion of the talk, then the design of an interplanetary vehicle habitat, and finally the water walls bioregenerative life support architecture. So this theoretical construct looks at the what was the conventional approach at the time I did this, which was, let me think, in 1990, where we were talking about expert systems for people. And basically the situation on planned for space station was that humans would service the machine. There'd be a human machine individual interface. The machines were put into laboratory racks. There were remedial ergonomics for these workstations by default. And basically the human services the machine, the laboratory environment supports the machine. And basically everything is about supporting the machines through a systematic or systems design process. Okay, next slide, please. So what I proposed was a participatory design, which I called systems for expert people, where the machines support human creativity for exploration and discovery. And that involves crew autonomy, crew democracy, and teamwork. And spatial habitability supports both working and social activities. Because there's a participatory architectural design process, the crew gets to play a role in helping to define what the design problem is and in responding to design solutions. And under this approach, the equipment and workstation design for productivity is designed for productivity, not for packaging, which is what we see in most habitable space architecture on ISS or in previous space stations like Mir or Skylab. The equipment is designed for efficient packaging, not for being an ergonomically well-designed workstation to enhance human productivity. And workplace design can shape the quality of work life, or it can make it much more difficult, depending on the approach that the architects take. Okay, so this early theoretical dichotomy or dialectic is something that we still need to implement in our space habitability and space architecture for the working environment. Okay, next slide, please. Now, the next thing I'm going to talk about is based on a paper I published called Testing the Celentano Curve. This graph you see here was by Celentano, Amarelli, and Freeman at North American Rockwell. Actually, at the time, it was called just North American Aviation. And what you see here is on the vertical axis, on the y-axis, is the volume in cubic feet. And on the right, on the x-axis is time in months. And their idea was that volume would follow a curve, volume against time would follow a curve that would level out at some optimal level or a so-called performance level or a tolerable level. And this is a very interesting construct that's had a lot of influence. And you can see that the three curves converge very close to the origin, but in this chart, don't actually pass through the origin. Now, NASA, next slide, please. NASA adopted an interpretation of this curve for the NASA Standard 3000 the Man Systems Integration Standard, and it's still actually in NASA standards. And the problem with it is that while the increase in volume does tend to follow a curve when it's plotted logarithmically, as you'll see, there's absolutely no basis for these three levels of optimal performance limit and tolerable limit. That's complete fantasy, but it's still in the documentation. And this is what it looks like if you actually plot the data that we have. The original chart was made in 1963, so this chart here is from 2008 and looks at all of the maxima for flights where it's pressurized volume per crew member in meter on the y-axis and mission direction in days on the x-axis. The yellow curve is a logarithmic plot, and the purple curve or line is a power curve. And basically, these two curves show the same thing. They're just really featuring different aspects of the variance. And you can see that the logarithmic curve especially does follow a curve similar to what Celentano et al. Showed, but it does not go anywhere close to the origin. And the power curve comes closer to the origin, but it does not pass through the origin either. And so this is another problem we have, which is that NASA and other agencies tend to cling to old concepts, old ideas. They don't take a scientific view of theory and data. It just becomes received wisdom by legacy. So anyway, does anyone have any questions at this time for either the crew productivity 2 slides or for these 3 slides? I don't know if I can hear anybody, but I hope so. No questions?
Yes, no questions yet.
Okay. I hope I haven't put you all to sleep already. Surely somebody must have a question out there. Okay, so now we're going to talk about the continuum of space architecture from Earth to orbit. And this first slide is a rendering by space architect Brand Griffin, who was working for Boeing. And this dates from 1982, so it's just over 40 years old. And what it shows is modules, very long modules actually, that are in a framework where there are long pipes, or what they call multiple berthing adapters. And these the modules, which you see have these 3 windows in front. Remember, Boeing makes airplanes, and so this is sort of like an aircraft cockpit for the crew to do their work in, to manipulate the robotic arm and other activities like that. But there are several problems with this scheme. Can anybody out there see a problem with architecturally with this scheme?
Mark, can you tell me, are you on slide 11?
I'm on slide 11, yes.
Okay, perfect.
Okay, nobody sees any problem. All right, so the problem is that once you put this structure together, you can't add any more modules or remove any of the modules, because the way it goes together, it locks in those modules, and there's no adding anything between the two multiple birthing adapters, between the two pipes. And there's a giveaway, which is one of the modules is up higher. It's not in line because they couldn't get it in after they assembled the pipe structure. One positive thing that Brand got in here that has eluded us on ISS is that he has a circulation loop, or what we called at the time a racetrack, where there's dual remote egress from each of the modules. So if there is a fire or toxic chemical spill or some other accident or problem, the crew has two ways to exit. So basically they don't have to go through a fire to exit. They can get out in the other direction. And similarly, if there's a problem with access to a module, the crew can come at it from either of two directions also. So here's another concept from 1982. This was a McDonnell Douglas concept done for Marshall Space Flight Center. The Boeing Space Operations Center was done for Johnson Space Center. So anyway, this one shows a very small pipe, multiple berthing adapter, and several modules plugged into it. And these are all dead-end modules. There's only one way in and one way out. And this actually kind of foreshadows what we ended up with for ISS. And that's because of the critical junction in designing the modules and the configuration. The lead was given to Marshall Space Flight Center in 1986. And this is what they would have done. And as it turns out, we have three nodes that in effect act as berthing adapters. Okay, next slide, please. We're going to slide 13. Now, here we're going to start getting theoretical. We're going to talk about the 5 platonic solids, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Now, these are essential geometric configurations for how we put structures together, and how we can put spacecraft together. What the concepts I showed you follow is the cube. Everything is orthogonal. Everything is at 90-degree angles, at right angles, as we say in English. And basically, they ignore the potential of using any of these other geometries. And I'd like you to take a look at the octahedron for a moment and remember it, because we're going to come back to the octahedron later, or at least the truncated octahedron. So anyway, next slide, please. We're going to slide 14. Now, there are different ways of conceiving of how these polyhedra are formed. And here we have Leonardo da Vinci's concept of representing the edges. So the ancient Greeks thought of polyhedra in terms of faces, but Leonardo thinks of them in terms of their edges, which would basically be their structural members, their struts. And so you can see again, tetrahedron, cube, octahedron, icosahedron, and dodecahedron. although he has them out of order from Plato a little bit, but there's nothing really systematic about it. Now here we have Johannes Kepler's duals, where he basically recognizes that there's a duality where if you look at the top row, octahedron and cube share a set of common points, where the octahedron's vertices touch on the middle of the faces of the cube. Similarly, the tetrahedron on the lower left touches on the faces of another tetrahedron. And on the right, there's a dual between the dodecahedron and icosahedron, where the dodecahedron has 12 faces and the icosahedron has 12 vertices. Now, there is a formula that describes the relationship of vertices, faces, and edges invented by the mathematician Euler. And this is the way Buckminster Fuller presents the equation. And he uses it in this chart, which he calls the comprehensively finite topology, from his book Ideas and Integrities. And I met him, well, I talked to him a number of times, but I talked to him specifically about this chart in 1982 or 3. And what he does here, on the left, you see what he calls the locally symmetrical shapes, which are just the tetrahedron, the octahedron, and the icosahedron. But then he shifts over, if you follow the green arrows, he shifts over the cube and he shifts over the dodecahedron in what he does next, which is that he reorders the Platonic solids from the order by the number of faces that Plato set them up, and he reorders them by the number of vertices. So you see that each of the duals switch places. So the only one that remains in the same place is actually the tetrahedron. And to me, this is a very profound change. Little noticed, but tremendously important. And what we have in terms of the meaning for a space station configuration is that some of the polyhedra are self-rigidizing. That is to say, they're triangulated, as opposed to having right angles, 90-degree angles, or obtuse angles, as in a dodecahedron, which are not self-rigidizing. Only the triangulated polyhedra are self-rigidizing. And then the second point is that having more vertices is good for a space station. And one of the problems we have on ISS is there simply aren't enough berthing ports for modules, for docking ports. And this has been a problem where the astronaut crews have had to move spacecraft out of the way so another spacecraft could come in. And there really isn't any berthing space left for new modules. So anyway, if you look at the ones with the highest vertex to edge ratio, it's the tetrahedron, the cube, and the dodecahedron. But the only one that is both self-rigidizing and has the high ratio of vertices to edges, it's tetrahedron. So I focused on developing a tetrahedral or triangular and tetrahedral space station concept. And here you see it, the patent drawings on the left, and a rendering by someone in James Polshek's architecture office did the one on the right. Any questions up to this point? I'm sure you all followed me perfectly. Listen, the only dumb question, literally speaking, is a question that's not asked.
Is there any means to improve on the tetrahedron that you could talk to us about?
I didn't catch everything you said, asked about the tetrahedron.
I was wondering if there's any means to improve upon the shape itself. So how can it be taken further?
Oh, yes, it can be. And I carried this project to a ridiculous extreme where I actually made a complete uh, circular segment out of a circular configuration out of basically 6 tetrahedra. And I don't show that here, but that was one of the concepts that grew from this. But the main thing is that you can have a lot of birthing ports on this. The moment you get away from 90-degree geometry, it opens up many possibilities. And when I was on the Space Station Concept Development Group in Washington in 1983 and 1984, and when they estimated the cost of the nodes as purely connective elements for people to circulate and for utilities, the cost estimate came out very low, came out at $50 million a piece, compared to the modules, which were a minimum of 200 million a piece, but in fact, in reality, have cost about $1 billion a piece. So slide 21, please. So here's another view of it's a longitudinal section cut through a module and a spherical node. Doesn't show all of the possible ports in the spherical node, but it does show the cupola. This is the patent for the space station cupola mounted to a radial port on a half hemisphere end of the space station module. And of course, it can mount on a radial port on a node as well. And that's essentially what we have on ISS today. So another aspect of this concerns the growth pattern. Here you see it laid out as a pair of triangles. And what happens is in figure 12A, we have the greatest asymmetry, but with the smaller mass, it's easier to handle asymmetry. But the assembly sequence needs to build towards larger symmetry, and that's what it does by the time you get to figure 12F. And that essentially predicted what the ways in which the ISS needed to be assembled. Now here's a rendering on slide 23, please. Here is a rendering from a NASA magazine of the way in which the Space Station Concept Development Group adopted the spherical nodes while retaining an orthogonal geometry, a 90-degree geometry. And it also shows the cupola in the node on the right. And so the nodes got into the configuration, but lost the advantages of the non-orthogonal geometry. Okay, number 24. So what happened to the spherical nodes? What happened was that after the Challenger disaster, the NASA administrator, James Fletcher, gave control of the space station configuration and the module definition to Marshall Space Flight Center. And they said, hey, we already have a prototype assembly set up for modules with conical end caps. And why don't we just stretch one or take the nodes and make it cylindrical? And then they wanted to stretch it so they could kind of turn it into a mini module. And they did that, but at the same time, they lost the geometric and assembly capabilities that the spherical nodes had. So this happened in August of 1986. And the node you see here is actually one that was manufactured by Alenia. I don't remember which of the three nodes it is. Okay, next slide to number 25. Now we're switching to a different project. This was a concept for an interplanetary vehicle habitat. And I'll go into detail about the habitat itself. But what I want you to look at here is on the lower left side, there are three structural panels, which are also water tanks. You can see in the color rendering, the blue structure are the water tanks with where the water provides radiation shielding, and then there's a blank square panel and a square panel with a pass-through hole in it, and then the other panel is hexagonal, and they're stellated. You notice that they have those creases in them because they fold a little bit to take up the curvature. So the geometric figure that the water tanks form is, wait for it, an octahedron. Actually, it's a truncated octahedron. Now, can anybody imagine why I chose a truncated octahedron for this configuration, for this habitat structure? Okay. I don't see
there is no
Yes,
because
go
there is
ahead.
no up and down, and so you don't need a flat ceiling and a flat floor.
Well, it's true there's no up and down, but that's not what which makes it possible to use non-90-degree, non-orthogonal architecture. It makes it possible, but it's not a major reason for going with a truncated octahedron.
Okay.
Okay, I'll tell you the answer. Okay, the truncated octahedron is the only Archimedean solid that has no triangular faces. The faces have only 90-degree angles, and I forget what they are, 120-degree angles. So there's no acute angles, there's no sharp angles in it. So this is a human factors consideration. We don't want these tanks to have 60-degree angles that are too sharp that could cut or injure a crew member. And I'll give you a close-up picture. Go to the next slide, please. Okay, so here's a larger view of the habitat. And the guy who had the question is correct, because this middle floor that cuts across the blue truncated octahedron can be a floor on both sides. Not that you're really going to use a floor that definitively in microgravity, but it can be a floor on each side. And then at the bottom of the lower compartment is the human-powered centrifuge, based on the human-powered centrifuge we built and operated at NASA Ames Research Center. Now, as far as providing further radiation protection, the stowage for food and equipment and all other supplies is positioned along the outer shell, the red shell. So all those yellow boxes is stowage of consumables and other supplies. And on the upper level, those partitions that are cut to match up with the octahedron, they don't look that good, but they are cut by intersection with the shell. Those are private crew compartments, and there would be the wardroom and galley in the other half of the shell, the one that would come out of the surface where it's cut. So please just speak out if you have questions. Right now, here's the last project I'm going to show you, which is the theory of space architecture water walls. And this was one of the early conceptual drawings of a functional flow diagram and a mass balance concept for how you control all of the inputs and outputs and internal processes of a bioregenerative ecological life support system. And there are 6 main functional flow, or I should say process units. From the upper left, there's algae growth, and then across to the right is urine and gray water processing. In the center is a power generation through an organic fuel proton exchange generator. And then on the lower left are solids for black water and organic to make organic fuel and fertilizer. On the right is air processing or air regeneration, air revitalization, which is to remove CO2 and generate oxygen as needed. And that one turned out to be the most difficult in terms of engineering. It really didn't work out the way we had hoped. And at the bottom is humidity and thermal control. So next slide, please. We're on slide 28. Now this shows a configuration, a cluster, a functional units cluster for each of those things with the same color coding. The blue rectangular boxes are the proton exchange electrical generators, and the green hexagons between the electrical generators are the algae growth modules or units. And the reason they're close together is that the algae need the fertilizer, the waste that comes off of the proton exchange electrical generators, fuel cells or power cells. Okay, next, please. Now, here's another way to look at it, which is what we call the process block diagrams, where there are, in this version, we had several other versions later. In this version, there's 4 main process blocks, which are block 1 at the top is climate control. Block 2 on the left is contaminant control, which is very important. Block 3 on the right is air revitalization using primarily, hopefully, cyanobacteria or blue-green algae and CO2 removal, which can be by algae or by electromechanical means. And then at the bottom, block 4 is power and waste. And at the center are the crew who have interfaces through respiration and waste generation and through taking in nutrition. These are their interfaces with the larger ecological system.
I have a question, if I may.
Yes, please.
It's a bit difficult to formulate, but is the complexity and the difficulty of designing these systems, has it very much to do with the financial aspect of bringing things into orbit? Can they improve significantly once economies of scale come into play? Can we expect a very dramatic change in how things are designed? That's the question, actually. Yes.
Well, you're right. The primary difficulty is financial, but the financial difficulty occurs long before we're ready to launch any of these things. The financial difficulty is getting enough money to do the laboratory work and to build these subsystems, because there's a lot of opposition within NASA to putting resources into developing bioregenerative life support. And that's a whole long story, but for a while there was a policy position against it. And the problem we face for, say, a Mars mission is that without a bioregenerative life support system, we don't know how to conduct that mission. We don't know how to keep the crew alive and healthy for 1,000 days. So the agency has really not stepped up to a realistic approach to sending people to Mars yet in terms of environmental control and life support systems. And the National Academy of Science has reported this, that the life support systems are not reliable enough and can't support a crew over such a long period of time. Continue with your question.
The question was, I understand that reusability will reduce cost of bringing per kilo into orbit, something like by a factor of 10, or if I remember correctly, or more than that. So does that mean that the design requirements will considerably relax? That was as in, are there technologies that can already be employed but are not feasible because they are too large or unapproachable, and can designers, as a consequence of this economy of scale coming into place soon, can designers relax a bit in terms of how they design habitats, or are they still constricted to this extremely efficient, miniaturized, compact, geometric design languages? I'm not sure if that makes sense the way I formulated it.
Yeah,
Do
no,
I have?
I understand. Your point is that these bioregenerative life support systems that are plant-based are going to take up large volumes, and yes, that's true. If you're raising food, if you're growing food to sustain the crew, where a significant part of the nutrition comes from fresh vegetables and hopefully someday fresh fruit, yeah, that is going to be bigger, and we're going to have to think of building bigger spacecraft and bigger lunar bases, and that is part of the issue, that these are bigger and heavier than the physical chemical life support.
And can we already begin to think in bigger and heavier, or should we still stick to the same constraints as we have to work with now?
Well, I think for a long time we're going to have both systems. We're going to have the physical chemical and the bioregenerative on the same spacecraft or in the same space habitat, because first of all, the bioregenerative can be prone to failure, and if for some reason you have plants or algae die off, you need to keep the crew alive, so you fall back on using the physical chemical life support. And the other thing is that physical chemical life support can fail, and then you'll be very glad to have bioregenerative life support. So, the bioregenerative will be uniquely capable of growing food, whereas the physical chemical cannot. I mean, both systems can do most of the same things in terms of air revitalization and water purification, and some of the contaminant control, but uniquely bioregenerative systems can grow food, and that takes a lot of volume.
Thank you.
Oh, you're welcome. Sure. Okay, so I think I have one slide left, which is
Marc, we have one
Yes.
more question.
one more question. Good.
Olivia, would you like to ask it yourself?
Yes, of course. I wanted to ask if there are any upcoming projects or areas of interest related in space architecture that you are particularly excited about.
Excited or terrified? Actually, I think we're going to see some very interesting work coming out in the next 2 or 3 years about lunar surface habitats. I think we'll see some real progress there, and I don't want to speculate about them too much, but I think that we will see some urban planning sorts of approaches, as well as interesting structural approaches, and hopefully some ISRU based ECLIS approaches. I think that's going to be the most interesting and exciting thing in the next few years. But I don't want to speculate on what the specific technologies would be. Okay, Olivia, did that answer your question?
Yes, thank you. I had another question. I was
Okay.
thinking about your opinion on the role of the architect in designing such complex systems and how these multidisciplinary teams actually work together. And where is the position of the architect in this? How do you see it?
That's a really tough question, because my experience is not representative of what I hope you'll go through. I had to fight the engineers all the way to do the work I did, but hopefully we've educated the engineering and management worlds enough that they're willing to work alongside architects and take advice and design leadership from architects. I hope we'll be seeing that. I expect we'll be seeing that soon.
Thank you.
Okay, you're welcome. So now we come to the last slide, which is number 30, or the next to the last slide. What this simply shows the research and other activity that we had to put together to try to carry forward the water walls. So it basically describes the research, the team members, and the funding centers. And if we had been able to win the NIAC phase 2, we would have been able to do some of these tasks, but we didn't succeed winning a phase 2. Although I could still go back and propose a phase 2, but it's a long, complicated story, and I'm not sure I will try. Okay, and now for the conclusions. Conclusions are that development of visionary space hardware benefits from a theoretical approach and constructs derived from that theory. So, stated simply, geometry is truth. And that's something I learned from Vic Vikyakal, the inventor of the AX series of spacesuits. Then a design solution is a hypothesis about the design problem. And human factors are intimately inseparable, untangleable from the pressurized habitable volume and its configuration. And finally, space architecture needs theory. This is the conclusion that I'm coming to, that design is the most fun aspect, and certainly for my first quarter century, I was all about design. But what we really need more than design is research, good research on which to base the designs. And finally, I'm coming around to seeing that theory as being very important and up till now lacking. And a lot of the designs we see coming out of government agencies and corporations is pretty unself-conscious. That is, that the designers, whether they're architecture engineers or whoever, are not really thinking about the larger implications and consequences of their decisions. They're just doing what's immediate and easiest to do with the least amount of effort and the least amount of cost, the least amount of developing new hardware. So I guess that's the end of my talk. Are there any more questions?
Yeah, I got a question about the designing and development of the modules, for example, for the space stations like the ISS. How much is it being influenced by those existing modules? Like, are there any restraints that you might find when you say, oh, okay, we got this new shape or form or measurements? It would be ideal in theory, but it just doesn't fit with the modules from the ISS.
Well, you're right about that to the extent that if you look at the Axiom space station, it copies as much hardware as possible from the ISS. They're not trying to do anything new or innovative. They're basically just trying to produce a version of the ISS that follows more along the lines of the Mir geometry than the ISS geometry. So they're not trying to do anything better or more creative. They're just trying to do something that's low cost, the lowest cost, and the least amount of effort to make a functioning space station. And that's what you would normally expect from a commercial entity, that unless there's some great economic or financial advantage to doing something new and different, they're going to stick with hardware that other people have spent the money for developing. But I'm sure that not all space stations will follow that approach. I'm sure we'll be seeing some more creative approaches.
Yeah. Do you see the possibility of old modules being exchanged for new ones? Like, especially in that case, you could say, okay, if the old ones are compatible with the commercial space station, then it might be worth to exchange for a new one.
I couldn't say, because the reliability of the hardware is a big issue. It's possible that somebody would change out a module. It has not happened yet, but it's certainly possible. And the Russians did it on the Salyut 6 and 7. They had a progress module that was not just for cargo, but it was sort of a little bit like a lap module, and they did change those out.
Okay. Thank you.
And kind of it happened a little bit with the Skylab station, right?
What about Skylab?
The Skylab space station that was built because the Saturn, one Saturn V stage was not used anymore.
Oh, yeah. Well, they built it from an unused Saturn IIb upper stage. Yeah, they had several of them sitting around not being used, so they were modified to be space stations.
I liked your question, Simon, because now when you look at this website of Axiom Space, it says headline building for beyond. And we are building next generation space use and next generation stations. And Marc just told us that they are just using modules that are already there without inventing new ones. So here is a conflict between what is said for selling reason, right, and what is done. And I think this is important to notice, because that's our time, that we have to look critical at things and see what's going on. And maybe that also, Marc, that could be a perfect entry point for architects, right? Because in order to innovate, architects are needed.
Right. Well, they actually have a space architect, Susanna Bianco, who was a graduate of SIXA, is working there, and she was on a team with me when we did the Antaeus sample receiving lab that would have been an orbital quarantine facility, sample receiving and analysis facility. And she's doing all she can to be creative and innovative, but it's within the constraints of using very ISS-like modules. They may be doing some different things on the interior. I don't know, but hopefully we'll find out soon what they're actually doing.
Yes, she's doing a very good job in her position. Also because she is communicating with the people there. What you said before, Marc, it's important to communicate your ideas to the engineers, to the scientists, to the managers, so they can understand what positive effects based architecture can have.
Yes, I hope so.
May I ask one more question, please? Just a quick
Sure.
question, since you sort of opened up a bit of room towards speculative space architecture. Are there any serious initiatives, not private ones, I mean NASA, into expanding on this whole new generation of generative AI and sort of assistant artificial intelligence towards, and specifically what I'm asking is, I see there's a lot of challenge and complexity having to do with accommodating a required number of astronauts who are all alive and all need a certain amount of food, and it's all snowballs. But obviously, if you reduce the number of required crew on long missions and you supplement them with as many complex advanced assistants as possible, then I imagine that would take space architecture a long way. And that's why I'm asking whether there has been any shift in this understanding of how many people and whether people are at all required in the immediate vicinity, and whether there are some concrete upcoming projects to that end.
Well, artificial intelligence, or AI, is a not very well known concept in terms of what it can actually do for design, not just in space architecture, but design anywhere for anything. What I see is that if you look at a spectrum from well-structured problems to poorly structured problems or ill-structured problems, AI is going to be most useful where the problem definition is well-structured, where you know what the boundaries of the problem are, you know what all the variables are, you can define the variables and the constants and the resources, and you have all this information available, and then you can let the artificial intelligence loose on it and run a billion iterations and come up with many alternatives, which then you can evaluate based on certain criteria that you establish. And in that setting, I believe artificial intelligence can help. If you're talking about a way outside the box problem, a very ill-structured problem, I don't see artificial intelligence being able to help that much.
I was rather, to narrow it down a lot, I was rather imagining a very pragmatical scenario where the habitat that has to function somewhere in orbit or on a station or a preparatory mission to increase the presence on the moon or somewhere, it would be designed for, I don't know, one person and simply artificial assistants, the kind that are advertised and being developed by Samsung and Tesla, but which are a few generations further and the other big manufacturer with a robot dog. Forgot his
Well,
name.
yeah, see, those are very well-structured problems. You know, if you're talking about an automobile, for example, or a washing machine from Samsung or whatever, a refrigerator, those are very well-known problems. You can give them very highly defined structures and requirements and capabilities, and then you can let artificial intelligence loose on finding ways to optimize or do something better. But you know, if you're talking about a habitat on the moon, first of all, where on the moon is it going to be? What are going to be your payload capabilities? What are your lander capabilities? How can you offload the habitat, or if it's an inflatable, the uninflated habitat? There are just so many of these things that are unknowns that make it a condition of irresolution and uncertainty. I don't know that artificial intelligence can help very much with doing things that are entirely new.
But it seems that a lot of the activities that that astronauts perform are quite repetitive, and at least as far as I read up on things, and it seems that sometimes you just need assistance to go through a set of routines and a set of tasks. And why I was asking this question was because I wanted to understand whether it's silly to, as a designer, to propose something like, okay, we will plan this new habitat or this new mission, and we'll have in the near future we'll have one person and 3 artificial assistants who are humanoid, and who I know that they are working on them. Even the pricing isn't so out there when I look at things and how much money is going into these things. You have $13 billion that can buy you the state-of-the-art aircraft carrier, or that can bring the OpenAI from 0 to where it is now. You can, and the NASA programs cost a few billion compared to that.
Let me try to frame the answer a little differently, which is that artificial intelligence is great to design or redesign something that's been done before, like an aircraft carrier. I mean, the United States is operating 12 aircraft carriers now, I think. And at the end of the Second World War, it had nearly 100 aircraft carriers. So this is something that's been built many times. But when you talk about something that people have never done before, and where there are a huge amount of unknowns, I don't yet see how artificial intelligence can help that much. It's possible that you can break down the problem into small enough pieces that artificial intelligence will help at a subsystem level. But I'm sort of remaining skeptical and waiting to see what artificial intelligence can produce where something completely new is concerned.
And so far, not what people design in space, but what people effectively do in space has not yet been choreographed to such an extent that it's a set of very predictable motions. So at this point, still the astronauts themselves need to be independent thinkers all the time. There is no reducing the number of astronauts that go there simply because they are so telegraphed in executing and so programmed. I had the feeling that that everything is choreographed in you know, with.
Yeah, there's a huge staff on the ground in Houston and in Moscow and in Beijing or wherever the Chinese headquarters is. Everything is planned carefully in advance by hundreds of people on the ground.
Thank you.
May I add to this discussion, Marc? Because yesterday I had a talk with Cheryl Bishop, and we had a similar question. That it sounds logic that when there is a problem, you find a solution. But the great challenge is to see the problem, right? That's the point. It is very hard to see the problem because, for example, when they built the Skylab space station, they never had experienced microgravity before. And I refer to the third conclusion, what you are showing us. Marc, I think this is vital for architects that you write a design solution is a hypothesis about the design problem, meaning one, right? One of many. So for example, for the Skylab space station, the designers built many solutions or experimented with many solutions. And this is where we are now, I guess, and where we need the creativity in space and on Earth. We don't know what the problem is. We cannot solve it with the things we have. We need to develop technology and we need to enrich it with theory. I like your talk very much, Marc. It's important to understand why things happen.
Yes. Yes, I agree.
And what you said to IA, you get a wonderful answer if you ask a wonderful question.
Yes.
If you cannot ask a question, you get not so usable answers probably. Do we have one question from the other students here? Otherwise, I would like to talk about geometry.
I have another question, a simple question, I think. But I always ask myself, how do you heat space models? Because space is super cold and you don't heat it with an open flame, do you? And so how do you heat it?
Well, there are primarily two ways. One is using electric resistance heating, and the other is heating a fluid and circulating the fluid and using that circulating fluid both to provide heat and to remove heat and reject it from through a radiator into the darkness of space. So those are the two ways. I'd say the primary way is through a thermal fluid.
Okay, that's simple. Okay, thank you.
You're welcome. Sandra, you wanted to talk about geometry.
Yes, I can't, because also now we work a lot with geometry, but there is a challenge because at least as long as I was studying and now that I teach, it has been less possibilities to learn about geometry and physics and mathematics. It was all cut from the curriculum in order to make it, more practical and more efficient. And now I see there is hopefully coming a little bit of so it's coming back because you need to know about physics. You need to know about geometry. You need to know about this mathematics in order to find innovative solutions. because what you showed can only be done when somebody has learned it, right? And tried and experimented with it.
Yeah, yes, I don't know who you're referring to that cut math and geometry from the curriculum. Are you speaking about the Austrian schools?
For us in Austria, yes, it's been cut all the time, actually.
Well, I wish I could help you with that, but
And also, I don't see what you showed. I don't see this work in contemporary space architecture. I can see it a lot in the work from the 80s. But I think currently there is not so much work done experimenting or developing geometric solutions.
no, there isn't much. Everything is cylinders and occasionally a sphere. And I think that's unfortunate that people are so limited in their imagination. And if your theory is correct that people don't do it because they haven't been educated in geometry, that's really tragic.
Have you, I mean, maybe the students can answer. Do you have extended know-how and geometric possibilities? I mean, could you follow what Marc was telling you?
I learned it in the higher technical college, but at the university I didn't hear it that often. Maybe in the first semester. Yeah, it's not a topic at the Technical University of Vienna.
We did have descriptive geometry at the Technical University when I did it. Also took a lot of geometry in preparation for the uni, but personally, I think more discouraging are the supposed design constraints that I already asked about, rather than the geometric the limitations of imagination coming to geometry. Personally, that's my feeling. So it's more of a discouragement on the part of the medium. It looks a certain way because everything is accounted for, rather than there's this much leeway and you are encouraged to expand in this way. That's my feeling.
I see. Well, I don't know, maybe space architects need a remedial math and geometry class. And that never occurred to me.
Yeah, it's probably, I mean, in terms of optimization, it could be a true benefit. In addition, of course, to what is interesting for me and what you also referred to, that the human factor is always untangible from the architecture.
Yes, this is true.
And that is also a challenge, because also referring to what Adrian said, humans are wetware, meaning it's hard to predict what they are doing at certain times or under certain conditions. So that's a challenge for an architect to design, in these limited spaces for human activities that are not easy to predict.
I see. Yes, humans can be very unpredictable, but a large part of astronaut training is teaching the astronauts or programming them to act in a predictable way. Because they have to be able to take training while they're in orbit and carry out complex tasks based on training they receive while they're in space. And it takes a fairly predictable person to be able to do that well. Because, training is based on people who have known capabilities and predictable behaviors. So, are there any other questions or comments?
I have one comment to what you taught us today. You say space architecture needs theory. That's true for architecture in any case, right?
Well, yes, to some extent. I'll tell you a funny thing with it. When I was in college at Princeton, they brought in a lot of people from faculty, faculty critics who came from Europe, and they would always ask, what is the theoretical basis of your design? And, the fact is that I don't know that every design needs a theoretical basis. I mean, if you're doing a simple house, does it need a theoretical basis? I'm not sure, but I know that in the larger concept, architecture needs theory, and urban planning needs theory, and space architecture needs theory in large part because it's so new, and it's a struggle to organize our thoughts in a consistent and complete way. So the way I would look at it is that a goal should be to take space architecture forward to the point where it doesn't always need theory. But right now it does.
That reminds me of an architect saying that he wants a habitat to be designed in that way that he should not think too much about the things he's doing in everyday life. He wanted a habitat, a structure, an environment that supports his activities. And maybe that is what you're saying, that space architecture needs theory in order that people don't have to think too much what they're doing and how.
Well, maybe in an ultimate sense, yes, but I think right now the problem we have is that not enough people are thinking about space architecture at abstract or theoretical levels. And I include architects, engineers, operators, and managers in that we need to be able to hold theoretical discussions talk about what people are doing. It shouldn't just be, well, we have a mold to make cylinders. Let's go with a cylinder. Period. We should be able to think much more deeply and broadly about what we're doing in creating spacecraft.
Probably needs to a budget for arts as well. Space architecture.
Yes.
But that's not an excuse. You can have a very good project and not have a budget. And you can have a big budget and a bad project.
Yes. We can see that with the SLS, huge budget, but it's too expensive for the Artemis program to fly it more than once every 2 years, which basically means they can't run their program. I don't know how long that can go on. A lot of people thought that SLS would be canceled a year or two ago, but it's still going.
So the good thing is that you are students and you don't have to worry too much about the budget yet. It's very important that you dream, innovate, and create. All right. I guess we don't have a questions. Do we have a question left?
I think on 3D printing, if it's realistic in that it will be employed in any foreseeable future. I know the projects and I've seen them. I worked for an office that developed 3D printed habitats for the moon and the Mars in architecture practice previously. But can we expect such things to be deployed anytime soon, or will we work with the conventional habitats that we take there and assemble?
Well, I think that you're right that there are going to be 3D printed habitats. There are a lot of people working on 3D printed houses and also on 3D printed habitats. And I think we will see them. I just completed a contract with the University of North Dakota for the design of a 3D printed spacesuit. I was specifically focused on spacesuit boots, but they have actually made 2 3D printed hard or semi-hard spacesuits. And in our next grant proposal, we're going to be going for much more advanced materials that hopefully will allow us to take those suits into the permanently shadowed regions at the South Pole, where the temperature is about 20 to 40 Kelvin, which is like minus 200 to 220 Celsius. Very, very difficult problem in materials, as well as the life support and thermal control, heating, and at the same time rejecting excess body heat.
Thank you.
You're welcome. Okay, I think we are coming to a conclusion here. Sandra?
Yes, I was muted. I'm sorry. I'm posting our spacearchitect.org link for those that are interested, because we have an excessive bibliography on space architecture related papers. If you're interested, I really would look for the papers from Marc Cohen. All his papers are wonderfully interesting, written, and really based on theory. And they have a lot of information in it if you're interested in it. And I thank you very much, Marc, for coming.
Sure. My pleasure.
And congratulations to the Gordon Woodcock Award again.
Oh, thank you. Thank you.
Thank you all. Have a good evening and have a good day.
Okay.
Goodbye.
Good evening. Good night.
Thank you.
Thank you.
Thank you.
Thank you.